All right, junior lab rats, this is lesson 4. Now, this one's going to be a little different because what I'm going to have you do is read through the lesson with me, and there are really not that many blanks. There are only, I think, 26 blanks, and a lot of them are very related. So you're going to read through the lesson with me, and then when we get to a blank, you're going to see if you either need to look it up or you can use some context clues to find the answer. Okay, so we're going to move right into it. Here's your vocabulary. Most of this is going to be defined throughout the lesson, so you'll be good to go for that. All right, so this is the little more of our earth science we talked about, how this is going to be in here. So I'm going to read, and when we get to a blank, we're going to stop and talk for just a minute, give you time to fill it in. You should be able to complete this lesson while watching this video, but you may need to pause a time or two to look some things up. So we're going to start here. The Earth and the Moon. Throughout history, the solar system has been modeled in different ways. Claudius Ptolemy, see how it's pronounced Ptolemy, was an Egyptian mathematician, astronomer, geographer, and astrologer who lived in the Roman Empire around 100 to 170 AD. He is well known for producing the most commonly accepted model of his time, the blank, or Earth-centered model. Now, there's your first blank. So we're going to stop for a minute, and we're going to have a look around this page and see we have a graphic here. And over here it says Ptolemaic model, geocentric theory. This is Ptolemy in the picture. And we have Earth in the middle and the moon going around the Earth and then the sun going around the Earth. In this model over here, it says Copernican model, heliocentric theory. And we have the sun at the center and then a bunch of different things revolving around the sun, including the Earth. And if you look, it has the moon revolving around the Earth. And this is a picture of Copernicus. Okay, so those are context clues you can use. All right, plus, if we keep reading to the next sentence, let's start back right here. We're talking about Ptolemy, right? He is well known, Ptolemy is well known for producing the most commonly accepted model of his time, the blank or Earth-centered model. Let's continue reading. In a geocentric model, Earth is stationary while objects in the sky move around it. Although incorrect, most people believed the Earth was the center of the solar system. Okay, right there you should have enough context clues to complete the first blank. And the second blank will follow very logically. Okay, so I'm just going to read. The blank, or sun-centered model, had been proposed as early as 300 AD, but it wasn't until 1543 that Nicholas Copernicus, a multilingual mathematician, astronomer, physician, classics scholar, translator, governor, diplomat, economist, and Catholic cleric with a doctoral degree in canon law, those are religious things, was able to prove that Earth and other planets revolve around the sun. So I'll give you a second to fill in that blank, but we're talking about Copernicus here, okay? And yes, the fish in my living room, that's his name, is Copernicus. And if you've ever seen Back to the Future, in Back to the Future, Doc Brown's dog's name is Einstein, but when Marty goes back to 1955, the dog's name is Copernicus. Again, great name. All right, so Copernicus, did this by using a mathematical model. Copernicus lived in what was then Royal Prussia, which we now call Poland. This is a typo, it should say both, and it says both with an E. Both Copernicus and Ptolemy are what are known as polymaths. This is just an interesting side note. A polymath is a person whose knowledge spans a diverse range of subjects. Other famous historical polymaths you might know include George Washington Carver, Archimedes, Michelangelo, Sir Isaac Newton, Benjamin Franklin, Thomas Jefferson, and potentially the best-known polymath, Leonardo da Vinci. Our solar system consists of the sun, planets, their moons, and a variety of smaller objects that mostly revolve in the same plane around the sun. The solar system is vast, and our lab for this lesson will help you understand just how vast it actually is. When measuring distance in space, we can't use feet or even kilometers. The blank blank, which is abbreviated AU, is used to measure distance of an object from the sun. Average distance from the Earth is 1 AU. Okay, let's take a second and let's look right here, look, there's two things. What's this? Get there in a second. And what's this? It says here Mercury is 0.4 AU. Okay, and the Venus is 0.7 AU. And right there it says Earth is 1 AU, Mars is 1.5, and so on and so on. Well, what's an AU? You have a key in the corner of your graphic here, and what's it say? AU is equal to something. Do you see what it is? That's going to go in your blank. Modern technology includes complex telescopes, piloted spacecraft, and even space probes. It has allowed scientists to explore the solar system. If your timing is right, you can even look up in the sky at night and watch the International Space Station pass overhead. That's the International Space Station. This website will help you find it. Okay, this is ISS right here. That's the International Space Station, and it revolves, it's in orbit around the Earth, and you can see it at night very well because it reflects the light on these solar panels, and it looks like this little glowing dot, and it flies through the sky fairly quickly. You can use the Spot the Station website, which will tell you when to go out and look for it. But also if you have the Skywalk app, which those of you who have siblings in the older class, most of them have the Skywalk app because we used it last year for a lab. If you have the Skywalk app, it'll also tell you where to look. Okay, and it's super cool. If you haven't done it, I highly suggest doing it because there's people up there, which is really wild. Have you ever noticed the lumpy bumpy appearance of the moon? The moon has some very recognizable features that you could see with the naked eye or low-powered magnification, such as binoculars. The major surface features of the moon are maria, highlands, and craters. Now, yes, this looks like the name Maria, but in reference to the moon, we call it maria. And here is a picture. Okay, now this is all context clues. Let's see if you can figure it out. Maria, highlands, and craters. Blank are flat, low plains that look like dark seas. The word maria comes from the Latin root for ocean. So what do you think might be a flat, low plain that looks like a dark sea if maria comes from the Latin root for ocean? So we're looking at maria, highlands, or craters. One of them is going to go in that blank. The blank are mountainous region. Okay, well, maria, highlands, or craters, which do you think are going to be a mountainous region? And blank are round depressions caused by impact from meteoroids, rocks, and rocks that travel through space. Okay, maria, highlands, or craters. Again, scientists hypothesize that the moon formed after an object caused an enormous collision with Earth early in Earth's history. So because the moon is composed of a lot of the same things that the Earth is composed of, that's what scientists believe, that some massive object slammed into the Earth, way before our geologic timeline even begins, the one that we looked at in our last lesson, and knocked a huge piece of the Earth off, which formed into the moon. Okay, so look in here. Now, you've got two graphics up here. Well, really kind of three. This is kind of two separate ones. So it says moon phases, and it shows how the moon looks different phases of the moon. First quarter, waxing crescent, new moon, waning crescent. Third quarter, waning gibbous, full moon, waxing gibbous. And then here, it shows you a solar eclipse and a lunar eclipse. And if you look at the solar eclipse, the sun is shining, it hits the moon, and the moon is casting a shadow on Earth. We had one 2 years ago. It was amazing. We were almost in totality here, and if you drove a little further north, you could get in totality, which we did, and it was incredible. Or you have a lunar eclipse when the sun is shining on the Earth, and the Earth casts a shadow on the moon. All right, so let's keep reading now that we've looked at those. The moon does not always appear round. The apparent changes in the shape of the moon are called, I wonder if one of those graphics might tell us what they're called. The moon's phases are caused by changes in relative positions of the moon, sun, and Earth as the moon revolves around the Earth. Okay, so basically what you've got here is a shadow. Sort of the same idea as an eclipse, right? All right. And blank, there's an and, so we know the next one's a vowel. And blank occurs when one celestial body casts a shadow on another. Okay, so in both of these examples of a solar eclipse and a lunar eclipse, you got one celestial body, that means one thing that lives in the sky, casting a shadow on another. So what do both of these have in common? They're both a type of what? Okay, so in blank occurs when one celestial body casts its shadow on another. A blank blank occurs when the moon casts a shadow on a portion of Earth's surface. I wonder what that could be. And a blank blank occurs when Earth casts a shadow on the moon. Once again, wonder what that could be. The moon affects the behavior of water in Earth's coastal regions. Tides are the regular rise and fall of ocean waters. Tides are caused mainly by differences in the moon's gravitational pull on Earth. So you've got the moon right above the Earth, and it's pulling on the Earth, and the Earth is pulling on the moon. The Earth is larger, so it's pulling really hard, but the moon is orbiting and trying to fly away from Earth, so there's tension between the two. And it causes tides to go, when the moon is closer, the tides go out because the moon is pulling the water towards itself. So if you live near a shore, that water is going to get pulled away from the shore. And if the moon is not near the Earth or not near your side of the Earth, it's on the other side of the Earth that night, then the water will be higher because it's not pulling that water away from you. So on to the solar system. Earlier we discussed how our solar system is vast. The planets nearest the sun are called terrestrial planets because their structure is much like that of Earth. They have a crust, mantle, and core. We talked about crust, mantle, and core last week. This word right here, terrestrial. Anytime you see like terra, this is this root right in here, or even sometimes there's an A instead of an E. That's a Latin root meaning Earth. Okay, so these are similar to Earth. These planets are Mercury, Venus, Earth, and Mars. They're the terrestrial planets, okay? They're also called the inner planets because they're nearest the sun, okay? Blank is the smallest of the terrestrial planets and the closest planet to the sun. Okay, which planet is the closest to the sun? Do you know? Oh, here's a picture down here you could look at that could help you. So blank is the smallest planet and it's closest to the sun. Blank's thick atmosphere is composed mostly of carbon dioxide, which traps heat and raises the planet's temperature. Blank's surface has a suitable atmosphere and temperature range for water to exist as a liquid. Blank shows evidence of once having a great deal of liquid surface water. Okay, stop for a minute. How many terrestrial planets do we have? Mercury, Venus, Earth, and Mars. Okay, now we know which is the smallest and the closest to the sun because we can look at the graphic. And this one talks about atmosphere. This one talks about water existing as a liquid. And this one shows evidence of a great deal of water on the surface once before. Okay, there's only one planet where water exists as a liquid. And I think you can figure out which one that is because you've seen water as a liquid. And unless you've traveled to space, I'm pretty sure you know what the answer will be for this one right here. All right, so now we know this one and this one. And they're going to be Mercury, Venus, Earth, and Mars. So we've eliminated 2. So now what we're down to is the one with the thick atmosphere composed mostly of carbon dioxide, which traps heat and raises the temperature, planet's temperature. And then this one, which shows evidence of having a great deal of liquid water on the surface. So whichever 2 you could always guess and throw it in a blank, or what you could do is Google and see what information you can find about the 2 planets that you didn't use, okay? So there's some study skills and test-taking skills going on here. This is important stuff. So if we move beyond Mars, okay, so we did the inner planets. Now we're gonna pass something else. We got this asteroid belt, okay? So beyond Mars, blank can be found orbiting the sun in the asteroid belt. Well, what do you suppose is in the asteroid belt? I wonder. Might be, something in the title of asteroid belt. Scientists now hypothesize that blank are remnants of the early solar system that never came together to form a planet. Okay, I wonder what that might be. Now, you could actually Google this sentence or these couple sentences and see if you can find the answer if you're unsure of what it might be. Beyond the asteroid belt are the remaining planets: Jupiter, Saturn, Uranus, that's pronounced Uranus, I know everybody wants to say Uranus, and Neptune, okay? These planets are called gas giants because they are composed mostly of blank and blank. I wonder. So you've got Jupiter, Saturn, Uranus, and Neptune. They're called gas giants because they're composed mostly of blank and blank. Okay, now you can Google that and see what answer you get. Gas giants are composed mostly of, right? These 4 gas giants are thought to have small, dense cores of metal and rock, but consist mainly of liquid hydrogen and helium. I wonder if we've seen this something very similar to consist mainly of liquid hydrogen and helium, anywhere above where we could use liquid hydrogen and helium as an answer. Again, context clues. Blank is the largest and most massive planet in our solar system. Okay, so we're Jupiter, Saturn, Uranus, and Neptune. All right, so here we go with our blanks. So which one is the largest and most massive? Well, you could look at this graphic and see if it helps, or you could look it up. All right. Where did it go? Blank is the most massive in our solar system. Blank's rings are the largest and most visible from Earth. Blank's rotation is tilted more than 90 degrees, and blank's bluish color comes from methane in the atmosphere. Okay, so what you need to know is which of these gas giants is the biggest, which has rings visible from Earth, which is tilted, and which is bluish. And you can look those up if you don't already know them. That would help you get the answers. And if you look right here, there are two with rings. So that's going to be tricky to answer if you don't know which one is you don't know which one is being referred to as the rings being visible from Earth. Okay, so what about Pluto? Pluto is much smaller and denser than the outer planets. In 2006, Pluto's status was changed from planet to dwarf planet. So Pluto used to be a planet back when a lot of books were published, but it's no longer a planet. It's a dwarf planet. It got ousted, poor Pluto. The nebular theory states that the solar system formed from a rotating cloud of gas. This cloud and all of its contents began to rotate, causing all of the particulate matter to come together in the center. So you have to envision this. It's really cool. You have this big cloud of gas. It starts rotating. All of the solid pieces kind of squish together in the center. All right? Pieces of this matter began to come together and form the beginnings of planets. The terrestrial planets are relatively small and rocky. In part, that is because the inner solar system was too hot during formation for ice-forming compounds to condense. The gas giants have large, low densities because the outer solar system was cool enough for ice-forming compounds to condense. So let's move on to the sun. The sun's energy is produced in its central region by the blank of hydrogen nuclei into helium nuclei. Okay, something happens where hydrogen turns into helium, and there's a name for it. Okay, let's keep reading. The sun remains stable because the inward pull of gravity balances the thermal pressure from nuclear fusion. Okay, if you don't know what nuclear fusion is, I suggest you look that up. That might help you out a little bit. The sun's interior, consists of the core, the radiation zone, and the convection zone. The sun's atmosphere consists of 3 layers: the photosphere, the chromosphere, and the corona. Features of the sun's atmosphere include sunspots, prominences, and solar flares. There's lots of cool stuff going on with the sun. So this gives you an idea of what's going on with the sun. And there are great graphics of the sun you can look up online, and I'll probably have some for you in class. It gives you some idea of what all these different things look like. And we don't need to get very in-depth because we are not studying earth science this year. This is just background information. So stars, okay? Astronomers classify stars by their color, size, and brightness. Other important properties of, that should be an S, stars include their chemical composition and mass. Bluish stars are hotter than red, and reddish stars are cooler. Same thing with flames, right? The bluish part of a flame is hotter than the reddish part. Most stars have a chemical makeup similar to the sun, with hydrogen and helium making up 96 to 99.9% of the star's mass. A star forms when a contracting cloud of gas and dust becomes so hot that nuclear fusion begins. There it is again, nuclear fusion. When the stars, I don't know what happened there. I think that's when the star's supply of hydrogen and helium dwindles, that means goes away, right? The star begins to die. It will become either a dwarf star, a neutron star, or a black hole, depending upon its original size. So these are all dead stars. But depending on whether the star was little, white dwarf, medium-sized, neutron star, or giant, black hole, is dependent upon the size of the star to begin with. So a blank is a group of stars, star systems, star clusters, dust, and gas bound together by gravity. What do we call that? Okay, let's keep reading. Maybe there's a context clue. Astronomers classify galaxies, galaxies into 4 types: spiral, barred spiral, elliptical, and irregular, based upon their shapes. Our galaxy, the blank, is a barred spiral galaxy. Okay, what's our galaxy called? If you don't know, look at the graphics below, okay? It says you are here. So this is our galaxy. And we are way down here on one of the arms, itty bitty. Our solar system is, how vast our solar system is, because we're talking about that today. And if you look, there is more than our solar system inside that little circle. So that gives you an idea of how big the galaxy is. And there's the name of our galaxy, which is what you need for this blank. Astronomers theorize that the universe came into being at a single moment about 13.7 billion years ago, in an event called the Big Bang. This is supposed to say in and. Boy, I have a bunch of typos today. After the Big Bang, the universe blank quickly. I wonder what that means. And then slowed down. Though the expansion is slower, it continues to slowly expand today. Okay, let's look at this sentence again. After the Big Bang, the universe blank quickly, and then it slowed down. And then it says here, though the expansion is slower, it continues to expand today. So what word do you think goes in this blank? And then here are pictures of the different types of galaxies. That's a spiral, a barred spiral like ours. See how we have there's sort of a line. You can kind of see it right there. That's what makes it a barred spiral, as opposed to just a perfect spiral like here. There's elliptical, just sort of an irregular circle. And that's the irregular one. It's just a kind of a messy looking blob. And then you are on to your questions. All right, so that's it. We are wrapping up lesson number 4, and we are about to get into our book reading lessons, which will change the way we've been doing our lessons so far. But, right now we're just trying to get some of these things done that will help us keep aligned with the other class. So when we get into lesson 5, as you're about to see, which is next week, it says right here, describing and measuring motion. And this is what you're going to read. And slow motion on planet Earth. So it says right here, you're going to read your textbook, 9.1 and 9.2. So our next lesson will not be a video. It will be an audio file of me just straight reading out of the textbook. Okay? You guys have done great work so far, and I will see you Tuesday.